So hello guys, welcome to Edule again, and we will be doing the longitudinal waves today, as you know. And again, this is the first time we are doing on Canvas, so there might be handwriting problems. So we will doing actually tudinal, okay, longitudinal waves. Okay, so longitudinal waves. So what is a longitudinal wave? Okay, suppose these are your particles of the medium. Hope you are able to see it. Actually, they are in a straight line. These are your particle of the medium. Okay, so this is say any medium, say air or water, and these are the particles of the medium. So your if your wave is always moving in this direction, as you can see, it's not necessary again. Oops, the line is not correct. If your wave is actually moving in say this direction, okay, the direction of propagation of wave, that is the propagation of wave, again propagation of wave, propagation is in wave is in this direction, then actually the what do you say, the movement of the particles of the medium will be to and fro. In the if they are vibratory, then it is always gonna be to and fro motion. But in this to and fro motion, what will be happening is that the particles will be vibrating in the direction that is parallel to the propagation of wave. Okay, that is the particle. If this is the particle, this particle will be actually go to this point and this come back to its original point. So this is the particle, it will go to this point and then it will come back to this point, that is to and fro, like this. Okay, so if your propagation is like this, the what you say, the movement of the particles is going to be like this, to and fro. As you know, they are just going to move, they're not just going to vibrate, they are not going to move. So the direction will be this. Okay, now let's actually visualize it in a better way. Okay, so yeah, again, medium is not gonna be like this, guys. Medium is not gonna be like this. Then only single layer of particles is gonna be like this. Okay, so if say this is again in most of your books, it is there. So you can even check this from that books. What I'm drawing is the particles of the medium. Don't worry, I'm just gonna explain it very soon. Let me just complete the drawing. Okay, in this canvas setting is the first time for us. So with time we will again, because I thought that the board setting was not very perfect or was not too professional. Again, particles, this was these particle drawing is little bad. Okay, so that is I thought. So okay, so drawing is just about to get complete. Okay, now see, these are these all are particles. These all are particles. Yes, particles of the medium, particles of the, if these are the particles of the medium, again, so these are your particles of the medium. So what's happening is in this portion that they are very close. Okay, and in this they are actually, we can say, far apart. They are far apart. Okay, so in this they are very close, and in this they are actually far apart. So so there's a change of what do you say, density or pressure. So what happens is actually, like I told, if the direction propagation of wave is in this direction, we just take this line, we just take, like in the example, we just took one example. So what is happening is that these particles are first actually pushing them, and then coming back. So what is happening when they when these three particles push these particles, what happens, these particles gets farther apart, and then what happens, these three particles come back close again. That is this motion. They first go, then return, then first go, then return, then first go, then return. So what is happening? They just push the particles that are far apart, and they just then come back. So when they come back, what happens? They come close to each other. Actually, there's a very big series of particles in this, so uh, that's why they are coming close. Unless they should also be farther apart, the gap should be maintained. But what is happening? In the if what while when they push this particle, we say that it is to and fro. So while pushing these particles, what happens, they come back, these three particles are coming back, but the gap should be maintained. Okay, but there are particles before them also, so that particles are also doing to and fro. So what is happening, at the same time when they are coming back, other particles are doing to and fro motion. In that to and fro motion, they come very close to each other, and in this to and fro motion, similarly to and fro motion is coming here, and the particles are from this space are going away. So there is a lot of gap between them is there. It's just actually, you can say, visualization of a this to and fro type of motion, coming back and going back, coming back and going back, coming back and going back. That is it is. Okay. Now these when the particles of these are very, what do you say, very close to each other, this is actually called as compressions. Okay, these are actually called as compressions. Compression is nothing but a region in where the particles are very close. We will just doing some more properties, and this is actually called as rarefaction. Not fraction, guys, mind it, just faction. Rarefaction. Again, with practice, the handwriting is gonna become better. So again, that is called rarefaction. Now let's have a look at the properties, what happens in the compression. Okay, so let's have a look at, let me just clear all this, and let me just let's study the compression. In this chapter, we in this time we will also only be looking at the longitudinal waves, guys. Okay, so we want to go very slowly. Compression. Okay, compression. Yes, compression. Now let's talk about compression. Let's talk about the properties of compression. Okay, the first property of compression is that, again, as these are the particles, they are coming very close. Okay, if they are coming so close, that means, that actually means there is very what do you say, high density, very high, what do you say, density, density. Now actually density is very high, higher than actually the normal. If this is actually considered to be a normal setting, if we take the example what we made. Okay, if this is a normal setting, even wider spaces there, then this is actually compression, and this is actually your rarefaction. Again, this gap is always uniformal, guys, because at least in a, what do you say, undamped wave, undamped wave is again that wave which does not loses its energy, and again that's not practically possible in, but again there's some waves which are undamped too. So again, very high density. Now that means the density is actually very high. That means the pressure should also be high, because if you compress the same particles in a very low space, if this is the original space and this is the new space, if, okay, so what is going to happen, as if you just imagine them to be placed in a container, what it, as they're very close to each other, pressure is also higher, pressure is also, oops, pressure is also high, pressure pressure is actually cursive is becoming better. High. Wait, yeah. Okay, so we will think that the pressure is very high. Now I can even prove you this fact that the pressure is gonna be high. Okay, your density, is actually equals to that is your density rho. Or let's just use D for the density, guys. Your density is again always what you say equal to mass upon mass upon volume. Okay, density is equal to mass upon volume. Now if we take these three particles, these particles, okay, what happens in these two conditions is again the mass is always going to be constant, because we are not, if you see, we are not going to add any particle, not we are even what do you say subtract any particle. So the number of particles is constant and the mass of a particle is always constant. So mass is equal to this. Mass is actually in both the conditions is constant. Okay, mass is constant, and as you can see, density if the in and density is high, that means mass is constant in both the condition. That means there is a change in volume. There is change in volume. Okay, now if we just take the what do you say the example of compression, what is happening is that if density is actually increasing, that means if your final say this increases, then actually your dominator should decrease. So what is happening is, as masses we are taking constant in both the conditions, in the condition of compression, the volume is actually decreasing. The volume is decreasing. Okay, it was very good cursor. Volume is actually decreasing. Okay, so your volume is decreasing. Now volume is decreasing. Now by Boyle's law, if you know chemistry, in chemistry there's a Boyle's law. Boyle's law. Again, first I am stating the law, and then we will see it without any law also. That what you say, pressure is actually inversely proportional to volume. So that means if volume is going to decrease, volume is what do you say gonna decrease, the your pressure will obviously increase. That is what is inversely proportional. Your pressure will increase, and that is what happening in this condition. Okay, now you only decide again if the particles are in bigger space. Okay, obviously there is a lot of space between them, so there's going to be less pressure, and when they are in very close to each other, then there is obviously what do you say very less space between them, and they are actually in a small volume, so pressure is also be high. So that is actually again force upon area. If area is gonna decrease, the uh, what do you say the pressure is gonna increase. Volume and area is, if we take a given example, we can also say the volume is directly proportional to area if we take height as constant. Okay, so that was with compression. And make sure 3 points about compression, that is a very high density, the pressure is high, and the volume is lower. Okay, so these were with density. The same is opposite way rarefaction. So let's study about rarefaction. Okay, so rarefaction, rarefaction. Okay, rarefaction. Now let me just draw the diagram of the rarefaction for you. Rarefaction is this. Okay, so my drawing is improving, yes, in just a 10-minute video. So again, by the I think the end of the chapter, it will be awesome. Okay, so this is rarefaction when the gap is actually when this what do you say gap is actually larger than normal gap, is larger than normal, I should make it better, is larger than normal gap. Okay, if the okay, so let me just confine it in a box. Sure. Oh, these are the particles, and no, if the a normal gap is taken to be like this again, if this is the normal gap, okay, this is the normal gap, that is the area of compression. Now you can again pretty much see that if we take the area in which it is, obviously the area is bigger and height is we have taken as constant, so the volume 1 of this, that is the volume of this, is actually bigger than volume of 2. That is, if this is V2 and this is volume 1 and this is volume 2. Okay, so now let's have a look at the properties that we were talking as. So the first property is that volume is highest. If we take example of all three cases, the volume is highest. Okay, second is obviously we know that pressure is inversely proportional to volume. So if volume is bigger, uh, or we can say if volume has increased, pressure is decreased. Okay, so we can say that pressure is, we can say that lowest, because now it is pressure is lowest, and obviously we know that pressure is okay sort of proportional, but we will not take just take an example. If we talk about density, isn't it? So what is density? Density is equals to mass upon volume. Again, if you remember this, I just said that it is Boyle's law. Pressure and volume are inversely, this is just gas laws, like pressure and temperature are proportional, directly proportional, volume and temperature are directly proportional, etc, etc, etc. Okay, so density is equal to mass upon volume. Volume is increased, sorry, density is also decreased, density is also lowest, density is low. So these are the three again things you should take care about. Rarefaction is just and it's not need to explain it much, because we have just explained it again in the case of what you say, explained it in the case of rarefaction. Things to remember, 3 points you should remember about. You should remember about their volume, you should remember about their pressure, and you should remember about their density, that is VPD or PdV, that's how you want to memorize this. But these three are the main things which actually what you say differentiate between them. In the next video we will obviously looking into the transverse wave. This was the longitudinal wave. So again, it is a area of low pressure here. Again, revise it. So let me just revise it. Compression is a area of high pressure and volume is lowest, I should say. Density is highest. Normal, not talk about normal. Okay, let's talk about rarefaction. This is highest, this is lowest, this is lowest. Okay, and if we talk about the volume, if this is volume 1, this is volume 2, and volume 3 is your what do you say, compression, then we can obviously say that volume 1 is bigger than volume 2 is bigger than volume 3, and the rest is all depends upon the volume. As you know, densities depends upon volume, pressure depends upon volume. So that's it this for this video. Next time we will be having a look at transverse waves. Thanks for watching.